Let's take a look at an example. Let's let v be the vector 3, 2, and d be the vector with components 4, -1. So for part A, we want to find the scalar component of vector v in the direction of d. So that is, we want to find the component of vector v onto d, or in the direction of d. For part B, we want to find the vector projection, or the orthogonal projection of vector v onto vector d. For this one, we want the projection of vector v onto vector d. Okay? Now, if you know the formulas, this is very straightforward. We just derived those formulas. So let's start with part A. We know the formula for finding the component of vector v in the direction of vector d is equal to, we take the dot product of v and d, we make sure d is normalized. We divide by its norm, because we don't care about the direction of d. By the way, this is one of the really useful properties of the dot product. If you take the dot product of a vector with its unit vector, and just to, as a reminder, this is the same as v dot d over norm d, exactly the same thing, based on the associativity of scalar multiplication with the dot product. We're taking the dot product of a vector with a unit vector. It gives me the component of this vector in the direction of the unit vector. One of the really useful properties of dot products. A lot of times when you use dot products in a formula, in an application, it comes down to this meaning. You can usually understand what's going on if you look at it from this point of view. Okay? All right, so this is simple enough to do. I need the dot product of vector v and vector d, so I'm just going to multiply corresponding components, then add the products together. So vector v, the first component of vector v is a 3. First component of vector v is a 3 times the first component of vector d, which is a 4. Now I'm going to add that to the product of the second components. Second component of vector v is 2. Second component of vector v, d is -1. And then I take the norm of d in the denominator. So that's the square root of the first component of d squared plus the second component of d squared. And so in the numerator, I get 12 minus 2, that's 10, divided by my denominator, which is going to be the square root of 17. So the component of v in the direction of d is 10 over the square root of 17. For part B, we need the projection. And we have lots of different formulas, but since we've already done the work for part A, we can calculate the component of vector v onto vector d times the unit vector pointing in the direction of vector d. So let's plug in. The component of v onto d, we just calculated that. That's 10 over the square root of 17. That's how much we scale the vector by. And then d over the norm of d, well, d is the vector 4, -1. And then we divide by the norm of d. We calculated the norm of d in part A already. It's the square root of 17. Okay. Now remember, when we divide a vector by a scalar, what we really mean is that we are multiplying by 1 over that scalar. So that's 10 over root 17. And instead of dividing by root 17, I'm going to rewrite it so it's 1 over root 17. times the vector 4, -1. If I multiply my two scalars together, I get 10 over 17 times the vector 4, -1. So now do scalar multiplication. Multiply each component of the vector by the scalar. I get 40 over 17 for the first component and -10 over 17 for the second component. Let me show you graphically what that looks like for this problem. Okay, so I've kind of set things up here. So we have vector v. This is the vector 3, 2. Let me zoom in so you could really see that that is vector 3, 2. We want to project it onto vector d. That means we want the orthogonal projection onto that vector d. The orthogonal projection means we just drop a line so that the line is perpendicular to vector d here. Okay. Our projection is how far along vector d our original vector v goes.